consider the following problem from the Math Prize for Girls 2011, a very high quality contest held at, I believe, MIT campus every year. So this is a geometric probability problem, and this problem is dedicated to one of my very good students, Daniel. The reason I'm dedicating this problem to him is because well, last time we solved a similar problem, we used calculus, and he protested for a long time on why we should be using calculus and whether there could be alternative ways to solve some of the problems. It was an HMMT problem, and if I have time, I can show you that problem as well in one of the upcoming videos. So what I will do here is I'll provide you two solutions, and you be the judge. One would be purely algebraic, and the other one using calculus. Awesome. So we have this equilateral triangle. Let's go ahead and just draw a sample one. So we have ABC, equilateral triangle. So we'll go ahead and choose a point somewhere on the side AB, and we'll label it as X. So X is chosen uniformly from the edge AB, and similarly you select a point Y, again uniformly from the edge AC, and you want to measure the length XY. And the question is asking for the probability of this length being at most this much. So we can use a standard law of cosine type of argument. This angle is 60 degrees because our triangle is given to be an equilateral triangle. So a law of cosine on triangle XAY will tell us that XY squared, the desired distance squared, is equal to, well, let's go ahead and call this distance AX as little x and this distance as little y, in line with the official solution. And obviously x can range from 0 to 1, and similarly y can range from 0 to 1 along the edge, right? So we can randomly pick the point y, anything from A all the way up to C, and there's no harm on assuming that our equilateral triangle, oh, actually it is given to be 1, so even better. Yeah, obviously. So therefore, yeah, okay, so we have, back to blue, x squared plus y squared from law of cosine minus 2 times x times y times this angle, which is 60 degrees, so cosine of 60 degrees. Cosine of 60 degrees, as you might recall, is equal to sine of 30 degrees, which is 1/2. So 1/2 and the 2 will just vanish. So therefore, xy squared, we have a formula for xy squared. So therefore, xy squared, the distance squared, is equal to x squared y squared minus xy, and we want to ensure that this distance do not exceed the square of this number. So squaring this will give you 1/√3. Awesome. So and that's it. So we want to figure the probability of this thing, right? So we want to figure what are the chances that this quantity on the left hand side is less than or equal to 1/3 when x and y are between 0 and 1, right? So x can be as little as 0 if x is actually equal to a, or it can be as high, it can be as far as b, in which case x is equal to 1. So in a sense, so this is a geometric probability problem because we can just draw another the coordinate plane with x and y. Obviously x and y live inside this square 1 0 1, just like any geometric probability problem. And now we need a sketch of this animal, right? So what would that be? Now this would be the topic of intermediate algebra, if you will. And if you have the AOPS series, I think it should be volume 2. Yeah, so what is this? Well, what I did is I cheated and I ran Wolfram Alpha to give me some clue about what it could be. I kind of was hesitant of what the shape looks like, and after I just realized that it was just an ellipse rotated 45 degrees counterclockwise. And that's it. So obviously our square here is a 1 by 1 square. I'm wondering about the area of the portion which is inside the ellipse basically. So back to our picture. So we have this ellipse which have this shape, green color. So obviously it is symmetric with respect to this axis. So something interesting happens actually if you test values. You just, oh, that doesn't, right? Well, okay, so what did I test? Well, first I tested what happens if x and y are equal. So substitute it. So you'll get 2x squared minus x squared, which is just x squared less than or equal to 1 over root 3. So therefore, if both of them are equal, this point here hits the value of 1 over the fourth root of 3. There you go. Some more comments. And interestingly, if x or y is equal to 0, strangely, so two of the variables drop, and again we have a similar number, exactly the same number, to be honest. So what it means is your parabola will go through these 3 points, not parabola, I mean hyperbola. So what? Hyperbola? I'm high. I mean ellipse. Okay, so the ellipse will look like this. Nice. So this is not a circle, that's an ellipse. So the probability, the desired probability, is the ratio of the areas, right? So the area of inside the ellipse within this square divided by the area of the square, but the area of the square is just 1. So therefore the probability, the desired probability, is the area of the ellipse divided by the area of the unit square. But the square has an area of 1 anyways, so therefore the ellipse. So what is the area of this ellipse? But ellipse is not a regular shape, right? So how do you find the area underneath the ellipse? Inside the ellipse, I should say. Well, at this step, there's a couple of alternatives. One alternative is to recall that there's a very neat trick on calculating areas inside the hyperbola. Why do I keep saying hyperbola? I mean ellipse. It's the following. I claim that if you have an ellipse with, you know that the ellipse will have a major and a minor axis with a center here and then 2 foci points, I don't know, maybe here and here. So it turns out that if you call this distance as A and you call this distance as B, the area within this ellipse would be, so the area, if you represent it, or let's just write it, area is equal to pi times A times B. And this warrants a little bit of an explanation, and it's where does this come from? It actually comes from a very neat idea, which is kind of very interesting. If you consider this circle, unit circle of radius 1, it is as if I'm stretching this circle in 2 steps. In the first step, I'm stretching it in the x dimension, and it becomes a very flat ellipse. And the area of this ellipse now is just because I stretched it in 1 dimension, and the radius was 1, but the half major axis is A, so therefore the area of the unit circle, which was pi, and after the first stretching becomes pi times A. But then further I stretch it in a second dimension in the y-axis, in the vertical, and then boom, I get the desired shape, but the factor of stretching is B, and that explains why we have the area of the ellipse the way it is. So, but how does it relate in our case? In our case, our ellipse is rotated 45 degrees apparently, right? So how do we take care of it? Well, one way to handle it would be to rotate the whole picture by minus 45 degrees. And after the rotation, we can Yeah, so we can deal with the desired areas by just this type of a stretching argument, if you will. Um, Actually, the more I think about it now, we don't even need to do any of it, right? Um, so all we need is, yeah, but I still need to figure by how much it is stretched. Yeah, it's actually, yeah, if I calculate the distance here, and then somehow I calculate this distance. Yeah, I think it's pretty doable actually, yeah. But okay, it's just a fun exercise to Yeah, I don't think I even need to rotate this thing at all. The more I think about it, the official solution rotates it, and it's not clear for some of you, I thought. So that's why I wanted to explain how that rotation is done. So how do you rotate a graph by a certain degree, right? Obviously, in the complex plane, we just would multiply it by CIS minus 45. But okay, let me just go ahead and show what you guys can do. So basically, it's hard to do a rotation on the with rectangular coordinates, but obviously there's an alternative representation which of any given point on the plane, on the coordinate plane, and it would be with a polar representation, and it's easy to rotate. So if you have a polar and you rotate it by whatever angle, for instance, in our case, we want to rotate it by minus 45 degrees, the new point would still have the same distance from the origin, except that the new angle would be theta minus 45 degrees, right? And that's it. So therefore, we can do the following. So starting with our thing, with our point, so r is just x. Sorry, I meant to say x is r cosine theta. All I will do is I'll just rotate it. Okay, let's just do it, I guess. So therefore xy, which is, well, let's do it in two steps, which is equal to r cosine of theta, comma r sine of theta. I haven't done this rotation business in a while, so let's hope that I'll get the correct way. So therefore, after the rotation, so rotate, the new point x prime y prime would be the following. Okay, I hope this is the correct convention. So it will become r times, so by this thing, so it will be r times cosine of theta minus 45 degrees, and then r times sine of theta minus 45 degrees, and that's it. So now at this step, I can go ahead and use addition formula. So r times cosine of theta times cosine 45 degrees, which is just root 2 over 2, I should say, times root 2 over 2, plus sine of theta, well, there's an r outside, yeah, there's an r here as well, so we can just factor out r altogether. Yeah, how about that? R is altogether factored out, and then we still have sine of 45 as well, comma, so we already took care of the r. So sine theta cosine of 45 degrees, which is root 2 over 2, root 2 over 2, minus cosine of theta times root 2 over 2. We can, in fact, even factor out the root 2 over 2 as well. But okay, so I'm not... oh, actually, let's keep the r inside. Because, okay, I remember. R times, R times, R times, R times. Okay, check this out. R times cosine theta, really? R times cosine theta by definition is just the point x. So that's just x root 2 over 2. X root 2 over 2 plus, and similarly, r sine theta is just y by definition. So that's just y root 2 over 2, comma, And then we have r sine theta again. This is just y root 2 over 2. And then minus x root 2 over 2. Whew. Okay, so that's it. So, but what's next? So next is you take your original equation and you try to express it in this format. If you are able to express it in this format, knowing that this is x prime and this is y prime, we have the new parameterization basic, the rotated shape in the x prime y prime plane. The only concern I have is, was I supposed to rotate it plus 45 or minus 45? Okay, so if the numbers don't match, so it means, yeah, it should have been the other way around. Okay, so back to business. So basically, you guys just take this thing. Okay, let's write this down again. So we just take it. So x squared plus y squared minus xy is less than or equal to 1 over root 3. Yeah, that's right, 1 over root 3. And somehow I want to make it look like this expression, which is basically, if you will, we can take out root 2 over 2 x plus y, and then root 2 over 2 y minus x, or yeah. So yeah, at this step you just make use of symmetry here. So for instance, yeah, can you guys confirm this result? Because so what you better do is you start with an root 2 over 2 x plus y, and you basically square this monster, and then you start with a, okay, so this is the part where it will get interesting. You need to put coefficients here, a here, b here, and then so luckily things should work out nicely. Y minus x here, y minus x. It doesn't matter because I will eventually square it anyways. So you could have written as x minus y as well, and that's it. And this less than or equal to 1 over root 3. Okay, so the idea is to expand these and then eventually find the coefficients a and b, and I think they come out as 1/2 and 3/2. Okay, a comes out as 1/2, b comes out as 3/2, and do the algebra, you should get exactly the same expression. So this is an alternative way to write this expression. So let me just go ahead and replace a with 1/2 and b with 3/2. So 1/2 here, 3/2 here. Well, you might say, hey, why did we even do that? So why did we already, an expression which is quite complicated looking, why do we even make it more complicated? Well, remember, this thing was just x prime, and that one is just y prime. We have exactly the same thing, x prime squared. So basically we have the new equation, right? I don't want to keep writing x prime and y prime. Pretend that we are just replacing with x and y, right? Come on, just get rid of it. Okay, good. So therefore, we can in fact multiply both sides of the inequality by 2 as well. So finally we would get, again, so instead of writing x prime here, I'm just writing x. So therefore the rotated picture will look like x squared plus 3 times y squared less than or equal to 2 over root 3. Okay, so that's, now this is way better, because this is the standard form of, well, almost the standard form of a of an ellipse. Obviously it is stretched, it's like a circle stretched, if you will, and the stretching factor in this case is just root 3. So how do you do the stretching? For instance, you can come up with yet a new substitution. Y double prime is equal to root 3y, and so therefore you would get x squared plus y squared, again replacing y double prime with y again, so less than or equal to 2 over root 3. Aha, and this is decidedly a circle. And well, okay, so that makes sense. So therefore we get a stretching of the circle indeed. Back to yeah, so Okay, so what's going on now? So we have in this new plane, the only problem remaining is we changed the coordinates. Rotating the coordinates, it also rotated this square as well. So that's not, there's no problem with rotating a square. However, okay, so when you do this substitution, the scaling thing here, the stretching business, it's going. Okay, let's do it in two steps. So in the first step, we made sure that the ellipse is horizontal now. So something like that. But then, because we rotated it 45 degrees, our square now looks like something like this and that, I think. And yes, what am I doing? No. Oh, so it's irrelevant. That part is irrelevant. Sorry for that. The part which is that's not even true, right? Okay, the part which is relevant is these lines, the y-axis and the x-axis. They put restrictions on our thing. Yeah. So instead of these two, I should have drawn, because I'm totally uninterested in what happens in the outside. So they become like this. Do you guys agree? So this is the 90-degree angle that in our original picture, right? So this 90-degree angle, and boom. So we have this picture, and we want to calculate the area here. So this is before stretching, where this one was if y is 0, x comes out as 2 over root 3. So this point here is 2 over root 3, and if x is 0, y comes out as, oh boy, this is not even 2 over root 3. This is something like this, if you will. Okay. So I don't need that. And then similarly for this one, if what happens if x is equal to 0, so you come up with something here. Okay, that's fine. But after the stretching, so these 45-degree angles here, because I'm stretching it back to a circle, it will look like this. Obviously, there's some technical details you need to fill in the gaps, please. So we now have a half circle, a semicircle. But what happens to these lines after we further push them by a factor of root 3? Well, that will become a 60-degree angles here. So wow, that's pretty neat. So this angle here is a 60-degree angle. That angle here is a 60-degree angle. So therefore, all we need is to calculate the area inside this circle of radius 1, and which is just 1/3 of the whole area. So therefore, obviously the radius of your circle is this monster here. I mean, this is radius squared. So oh, actually, which is good news. So therefore, which is just pi r squared, right? So pi times 2 over root 3, but we only want a third of it. Okay, so this is just 2 pi over 3 root 3. This is after stretching, like after we compress the picture. Now we need to expand it back. So, but because the compressing was by a factor of root 3 in one dimension, all we do is we multiply it by root 3 when we go back to the original shape, and then this area obviously is exactly the same as this area, and boom, so we would be done. So therefore this would give us a wrong answer. Again, I messed it up. 2 pi over, I thought I was supposed to get 2 pi over so I stretched it. Oh, so look at how I defined the new variable. So the new variable is I stretched it, I expanded it, I didn't compress it. I expanded it on the y-axis. Oh boy. Okay, so because I was lazy to calculate this point here, apparently I did it like this. That's how you do it. Okay, got it. So we expanded it by a factor of root 3 to get a circle here. Yeah. And then now I need to compress it back. So which is 1 over root 3. Yeah, the factor is, yeah, just check the official solution, I would say. 1 over root 3. Yeah, and then boom. 2 pi over 9. Okay, so that's what you would get. Now I would like to provide you an alternative way to solve this problem directly using calculus. And the idea is this very neat observation that so the area here is just two equal portions. We have one portion here above the 45-degree line, and then we have one portion below the 45-degree line. So all I will do is, let's just focus on the portion above the 45-degree line. I'll calculate the area of this quickly using an integral. In order for me to do that is, obviously here y is implicitly defined. I need to find a closed form formula for y, and for that I will be using the quadratic formula. And once I have the quadratic formula, it should be very convenient to get the desired result. So let's go ahead and use the quadratic formula to make the calculation. It's a little bit nasty work, but I mean, hopefully, if you do follow the algebra, it's not, well, yeah, I mean, I think it's equally hard, both methods. But anyhow, so you get y squared minus x times y. Remember, here x is treated as just a constant, plus x squared minus 1 over root 3, if you will. And so I want to, so this is the constant term, this is the coefficient of the linear term, the y. And so when I apply the quadratic formula, so it would be x minus b, so which is minus x, plus or minus, and down the road I will just get rid of the minus one, which will be the lower half. I'm not interested in that one. Square root of, okay, so this one is bad, x squared minus 4 times x squared minus 1 over root 3, and that's it, all divided by 2. And that would imply that y is actually equal to x over 2. We can factor, and well, we don't have to. Okay, let's just not do it. Okay, so plus, we have still 1/2 here. Oh boy, I hope I didn't mess up. Okay, so square root of, so we have x squared minus 4x squared, so that will be minus 3x squared, and then we have a plus. So 4 over root 3 plus, sorry, minus we said, right? So minus 3x squared. Oh yes, so that's pretty good. Now let's do the integration. So basically the only thing you need to know is the following. Well, two things to know. If you have two graphs, like one function like f of x here above another function g of x, and you want to calculate the area between these two functions on a certain range, the idea is to make calculate the following integral from a to b. That will give you the desired area that you want. So we just observed that our ellipse is totally above the 45-degree line in this picture, so the ellipse is fully above it. So for that reason, and we already calculated this point, right? So it turns out to be 1 over the 4th root of 3. All you do is just set x and y equal to each other, because this is the 45-degree line. And then we're ready to go. So let me go ahead and write the appropriate integration. So therefore the desired area is equal to 2 times, because 2 times the yellow part, 2 times the integral of the one above. The function above is our function, this monster here, x over 2 plus 1/2 square root of this weird expression minus 3x squared minus the one below. The function below is the y equals x. Nice, and that's it. We just calculate the integral of this from 0 all the way up to 1 over the 4th root of 3. Well, obviously you have x over 2 here, minus x here, so that will give you a minus x over 2, but then you will eventually multiply it by 2 again, so that will give you the integral of Well, okay, let's just do this one first. The 2 and the 1/2 will cancel, so it's just the square root of 4 over root 3 minus 3x squared dx. And I won't bother writing these. And then minus, so we decided with x over 2 times 2, it's just minus x. The integral of x dx. And at this stage, so what we can do is, yeah, we can calculate them separately basically. So the second one is quite easy. So this just the integral of this is just x squared over 2, and all you will do is you will just plug in the boundaries. So 1 over the 4th root of 3 here. Yeah, so that would be very straightforward. Okay, so the part that's kind of a little bit more nasty is the other part. So the first part. And for this one, I have my calculus book in front of me. So this is the one that I have right now in front of me is by the single variable calculus, the 6th edition. I'm sure this book is now probably in the 10th or 12th edition. The title of the book is Single Variable Calculus, Early Transcendentals. And like most good calculus books, either in the front cover or in the back cover, you have useful integrals. And so the one that I have is at the back end of the book. And there is a formula for this one. So let me open some space here. The integral of the square root of a squared minus x squared dx. Well, this integral is apparently equal to, I had no clue before this one, before attempting to solve this question, x over 2 square root a squared minus x squared plus a squared over 2 sine, actually the inverse sine x over a, arc sine x over a, and then the constant. Obviously we won't need the constant because we have a definite integral here. So therefore in our case we have this 3 business which is annoying. So what we can do is we can factor it out of the integral. So if we factor out the root 3, so what we will be left inside the square root is, because we factored out a 3, there will be a 12. No, 4 over root 3 root 3, yeah. 4 over 3 root 3 here, and then minus x squared. Now this is nice because it's in the desired form, right? So we will call this guy, this monster will be our a squared, if you will. All right, so we are on a good run here. So root 3, the integral here is apparently, I'm directly writing it. I have no clue how they came up with this. I'm sure they are using some trigonometric, well, actually, I kind of have a clue. I don't think it's too hard, to be honest. So you just do a substitution. You replace x with probably sine theta or something like that, and then you substitute back in. Well, before you do that, obviously you factor out the a outside, and this one will reduce to x over a squared, and boom. So you should be able, so it should be fairly simple. But okay, so back to our story. So therefore, and then we want to just directly plug in this one, right? So because the other one is just 0 anyways. If you want to, I can directly plug in, so we can cut it short because the video is already pretty long. So plug in the x, which is 1 over the 4th root of 3. This is nasty. And then we have a 2 divided by 2 as well. So 1 over 2 times the 4th root of 3. That's a times. Square root of pretty much the same thing. So just keep whatever was inside earlier. Minus x. X is the same monster. X squared actually. So which is just 1 over the square root of 3. Plus a squared over 2, which is just our thing, so which is 2 over 3 root 3, 4 over 3 root 3 divided by 2, and then sine -1. Okay, this one is interesting. So x is just the 1 over the 4th root of 3, all divided by a. A is just the square root of this monster, which I will do it in 2 steps. It's just 2 over the square root of 3 root 3. There you go. Whew. And don't forget this monster here too. So minus what is that? 1 over root 3 after squaring divided by 2. 1 over 2 root 3. If I'm not mistaken, I might as well be. Well, I tested it earlier, it worked, so I hope I can recreate this whole result. I think I already messed up. Where did I mess up? The integral, I'm multiplying it by 2. Okay, so let's hope for the... Yeah, hopefully it should work out. Okay, let's double check this. But it's along these lines, so basically. Alright, so when you multiply the first one, you'll get 1 over 2. Actually, in the numerator, you are left with some expression, not in the denominator. The fourth root of 3 divided by 2. And then inside this, we have, this is the square root of 1 over 3 root 3. Okay, so this is nasty. 2/3. Okay, so the sign to the -1 power. So we still have this thing, 4th root of 3 in the numerator. In denominator, we have 2 over, again, the same story. This is just root 3 times 4th root of root 3. The reason I did that, because these two will vanish. Minus 1 over 2 root 3. Yeah, it would be a shame if we can't get the correct answer after so much work. And then this is 1 over root 3 times the 4th root of 3 plus 2/3. Okay, so what's left inside is 1 over... No, root 3 over 2. So the sine of angle 60 will give you root 3 over 2. So this is just pi over 3. And that's nice. That's pretty much the answer, actually. But why would these two cancel? Please, God, please let them cancel. 1 over 2 root 3 minus 1 over... Yes! 2 pi over 9. Hey, how about that? So we solved the same problem using calculus, Daniel. And then we got this result earlier as well, rotating and then stretching ellipses. Yeah, that was, I think so. So where would I put this question? Is this an AMC 10 question? Definitely not. This is no way. Maybe AMC 12. I think so, yes. I've seen AMC 12 questions which use hyperbolas and ellipses in the past. I don't think we can expect anything in the AMI like that, to be honest. Yeah, if anything, this is more like an AMC 12 type of problem, where only just a few people can solve it in the given time, because how are you supposed to solve all this in 3 minutes, right? So that doesn't make sense. But yeah, so that's it. Hope you enjoyed the video and looking forward to see you guys in our next lecture.